So I'm not sure what should I say? Maybe good morning, and good afternoon, and good evening, everyone. So my name is Rifan from Tongji University. I very much appreciate Peter for the invitation to give this talk because I can share some of what we achieved over the past several years. Mainly for the last like 3 to 5 years, from my PhD to postdoc and to my faculty areas. My research interest, I just put a brief block diagram. So my research interest includes both the theory and applications of computer vision, machine learning, and also image processing. For applications, I'm particularly interested in autonomous driving perception, especially for perception, and road condition assessment, and also clinical diagnosis. So today I will mainly discuss, let me see whether I can use it as a pointer. I will mainly discuss 1, 2, 4, and 5. Maybe next time I will share my research outputs for the clinical diagnosis. We mainly did the clinical diagnosis at UC San Diego. So I just drew a big picture of my talk today. I will first introduce two main components. One is autonomous driving perception. The other one is road condition assessment. For autonomous driving perception, we'll have like 3 sections. The first one, 3D information acquisition, including optical flow estimation, stereo matching, surface normal estimation. And then we'll discuss semantic segmentation for Freespace and anomaly detection. I put lane marking detection here, but we didn't use semantic segmentation here. So maybe I put something wrong. So finally, I will introduce something for object detection, mainly for parking violation detection. I mean, the illegally parked car detection. As for road condition assessment, we'll have like 2 main components. So we'll have like 2 steps. The first step is to get the 3D information, like the 3D road information. So the first step will be road 3D imaging, and second one will be road damage detection. So to detect like potholes and cracks and etc. So today I will mainly discuss how to detect potholes, because pothole is more important than the crack detection. So autonomous driving perception. So I will. First, I draw a picture for a typical autonomous driving system. So you can see that it includes like 3 different parts. I put like in 3 different colors: the blue colors, orange color, and also the green color. So it consists of 2 main components: the hardware and software. Hardware is the blue colors, for example, like car sensors and car chassis. So car sensors means like, for example, like LiDARs, cameras, IMU, etc., like GPS. Well, for the software, well, we have like 4 main components, like perception, localization, mapping, prediction, and planning. In some cases, we also need to communicate with other cars. For example, like autonomous driving, we use 5G network to communicate with other autonomous driving cars to avoid collisions. So for this kind of typical block diagram, we can draw in some different other ways. Some people may say like perception and localization and mapping should be considered together. So this is kind of taxonomy in our group. I also put a QR code. You can scan this one to get my book chapter about this autonomous driving system. For the perception module, typically I put some standards here. So it tries to analyze the road sensor data, for example, like RGB images or LiDAR point clouds, and outputs the environment understanding. That this kind of understanding will be used by other modules like SLAM, like localization and mapping, prediction and planning, and also control. So for the second part is the localization and mapping. It tries to localize the autonomous driving car, and also it tries to build and update 3D environment map. For prediction planning, we put together. So typically there are 2 different tasks. One is to predict, and then the 2 predicts other autonomous driving cars or other cars and pedestrians. And for planning is to give you a safe trajectory. Finally, we will have like a control module. This kind of module will send appropriate comments to the car chassis based on the prediction and planning module. So it will based on the predicted trajectory to help the autonomous driving car to navigate safely in complex environments. So to get 3D information, so we should use different multiple views. So I put two different examples here. The first one is still camera. The second one is a single mobile camera. So for still camera, because we have two cameras, one is on the left, the other one is on the right. So we can get two different views. And then we use these two cameras to get the 3D information. And similarly, we can also use only one camera, but the camera is mobile. So the camera at different locations can get different views. So we can also use a single mobile camera to get 3D information. But you can find that from this figure, the miracle to obtain the 3D information is to get multiple views. And the most important objective is to solve the correspondence matching problem. So we need to estimate the correspondence. So we need to detect and match the correspondence between different views. So today I will mainly show like 1, 2, 3, 4, 5. So I will mainly show 5 different algorithms. One unsupervised optical flow estimation algorithm, and 3 stereo matching algorithm, and also 1 surface normal estimation algorithm. So this is the kind of taxonomy of 3D information acquisition, but there are also some other types of 3D information like thin flow and the elevation maps. I only put 3 different types here. For example, like supervised method, I put some like supervised optical flow estimation and supervised stereo matching. The supervised method have achieved compelling results over the past several years, especially with CNNs and also recently with transformers. But this kind of method typically require a large amount of well-labeled training data to train the networks. But in some cases, especially for autonomous driving, sometimes it's very hard to get the ground truth labels. So my group is more interested in unsupervised learning and self-supervised learning because we do not need to rely on any ground truth labels. For optical flow estimation, I put some like preliminaries here. So I put some like images, RGB image, and also optical flow image. So it will be like the optical flow image will be a 2-channel video feature, video information. So it has 2 different channels. The first channel is FU, the second channel is FV. So FU means the horizontal positional difference. The FV means the vertical positional difference. So optical flow estimation will be a 2D search problem. In the last year, we proposed CoT-AMFlow. It's an unsupervised optical flow estimation approach. In terms of the network architecture, we introduced an adaptive modulation network to remove outliers in challenging regions. But in addition to the network architecture, we also developed a new training paradigm. It is called co-teaching strategy. So we have 2 different networks to teach each other about the challenging regions to further improve each other to get the better accuracy. This figure shows the AMFlow architecture. So AMFlow is for self-supervised optical flow estimation. Here you can see there are 2 important components. One is FMM. The other one is CWM. FMM means flow modulation module, and CMM means cost volume modulation module. So flow modulation module refines the flow estimation from the preceding primate level using local flow consistency. The cost volume modulation modules reduce the outliers in the cost volume using a flexible and efficient sparse point-based scheme. So this figure shows the co-teaching strategy. So it's a very interesting strategy. Typically, we have 2 networks, but these 2 networks have the same architecture. We call it, like, for example, like network A and B. They have the same architectures, but they are initialized with different parameters. I think I can use another example to explain this. So for example, there are two students, and they have different knowledge about their homework. So student A knows some like answers, and then they can, for example, he can answer some questions, and student B can also answer some other questions. So they can do their homework by themselves, and then they can exchange their confident answers. So they can know, so they can make some programs simultaneously. So this kind of co-teaching strategy. Here are the experimental results. So the significantly improved areas are highlighted with the green dashed boxes. I didn't follow the latest unsupervised method, but upon the publication, our method achieves the best performance for unsupervised method on 3 public datasets. And you can see our method outperforms all other SoTA and supervised methods except for these 2 matrices. And our method can also perform better than many supervised methods, including like PwC net, live flow net, V1 and V2. And of course, Raft is the best paper for ECCV20, if I remember correctly. So Raft performs better than ours. Because Raft is a kind of supervised method. Here's a demo video for our CoT-AMFlow algorithm. We evaluated our method on 3 different public datasets. You can also find this YouTube. You can also find this demo video on the YouTube. And you can also find our paper by scanning the QR code. I'm not sure whether you are interested to share to scan the QR code, but it's, I think, a very easy way to share some papers. So we mainly compare our method with AR-flow, SoTA method. And you can see that our method performs robustly near the boundaries. For example, like the tree boundaries, car boundaries, like the road boundaries. This is one, I think it's KT 2012, I guess. This is only for testing. So we have a training set, but this demo videos are only for testing. For optical estimation, it's very important information. Optical can be used for dynamic object detection. So typically, we try to use optical estimation as a kind of front end and to improve other modules like SLAM. In addition to optical estimation, I also want to share something about the stereo matching. So as mentioned above, the objective of 3D reconstruction is to solve correspondence matching problem. So one stereo camera is not calibrated like this one. I just changed the notations here. So it will be like 2 different cameras. L means left, R means right. So it will be left camera and right camera. So if the stereo camera is not calibrated, the correspondence matching problem will be a 2D search problem. You can see the correspondence matching will be the correspondence will be on the epipolar lines, but these 2 epipolar lines are not collinear. So we had to do 2D search problem. We had to do 2D search. So when doing stereo matching, typically we do stereo rectification before doing stereo matching. So these 2 images, you can see it is 2 blocks. The black blocks means the original planes, and the red blocks means the rectified planes. So after doing stereo rectification, the epipolar lines will be collinear. So this correspondence matching problem will be a 1D search problem. So recently, we just developed a supervised method stereo matching algorithm called SCV-Stereo. SCV means sparse cost volume, sparse cost volume. So it's capable of learning dense stereo matching from sparse cost volume representations. So it is based on some hypothesis from some kind of inspiration from these traditional methods. For traditional methods, typically the stereo matching is very time consuming. So we typically use a sparse cost volume. We only estimate the disparities for several pixels. We do not estimate the disparity for the whole pixels, for the whole search range. So we bring something from the traditional methods to develop this kind of algorithm. So if with this kind of algorithm, we won't need too many stereo matching search range. So we can simply update disparity estimations in an iterative way. Here are the experimental results. So you can see that our method from this kind of two figures and from one table. So you can from this figure, we highlighted some like greatly improved areas. And from this figure, you can also see here. This one is inference time. This one is the I think the error. So our algorithm achieves best trade-off between speed and accuracy, and also it performs many. It outperforms the SoTA supervised methods. We put some demo videos here, but I think I need to change my data pointer. So we typically we mainly compile our method with PSM-NET. If you are working on a stereo matching, you should know about PSM-NET. It's one of the most SoTA methods for stereo matching. And you can see like our methods form robustly on the car boundaries and also the road boundaries. But this one, I think, is a supervised method. So if you want to deploy this one algorithm on some kind of real-world applications, for example, like autonomous driving, it's a bit hard because you still need to get the ground truth to train the models. So this is why we borrow something from the optical flow estimation. We borrow the co-teaching from the optical flow estimation to do the stereo matching. So typically we change the network. The previous network is used for optical flow estimation. So we change the network for stereo matching. So we developed another algorithm called CoT-Stereo. It's an unsupervised method. So it's similarly, so it's used co-teaching strategy to use two networks. These two networks have the same architecture to learn stereo matching with each other. So it's kind of in a supervised way. So you can also see that our algorithm can bring a lot of can bring some significantly improved areas. And also, we draw a similar figure to show the trade-off between speed and accuracy. And our CoT-Stereo also performs better than the SoTA algorithms in terms of trade-off between speed and accuracy. This is a demo video. I think I need to click. So we mainly compared our method with SSS and NET, with SoTA unsupervised method for stereo matching. You can see from this video that CoT-Stereo performs a little bit worse than SCV-Stereo, but it's still enough for some autonomous driving applications like lane detection. But it does not require any ground truth labels. So we mainly evaluate our method on the KT-Stereo benchmark. We evaluate our method on KT-Stereo 2012 and 2015. Let me move forward. So in the last year, we developed another algorithm called self-supervised learning. It's called self-supervised stereo, called PV-Stereo. But unfortunately, this algorithm was submitted to I can't remember, should be Intelligent Vehicle Symposium. And then we submitted to transactions and still rejected. And finally, it got accepted by robotics and automation letters. So this one is based on, it's inspired by the traditional methods. So we developed a kind of called pyramid structure based on the traditional method called pyramid voting module. I draw it here. So TSM here, let me use a data pointer. TSM here means the traditional stereo matching algorithm. So we build two pyramid. The first one is the left pyramid, and the bottom one is the right pyramid. So we try to use two different pyramids to get different resolutions of stereo images. So our hypothesis is different resolution of stereo images can provide different disparity maps, and also the most confident disparities are consistent for different resolutions. So we use a traditional method to get some ground truth pursuit labels. And then we use voting, and then we use like a left and right consistent check to get a kind of pseudo labels, and then we use this kind of pseudo label to supervise the to use as a ground truth label to be used by another supervised method. So when training this kind of framework, you do not need any ground truth label. You only need to two input, like left image and right image. And then you can use this kind of PVM module to get ground truth and to get this output.
Can you return the process again?
Oh, yeah.
So the left pyramid, the right pyramid, what is the difference between them, first of all?
The left pyramid is from the left image, and the right pyramid is from the right image.
And both are the same type of different resolution scales. And then
yeah.
And TSM, what are the initials again?
TSM means like traditional stereo matching. It's kind of, for example, like local stereo matching algorithm. And then we can use this kind of algorithm to provide some kind of pseudo labels. And then we use pseudo labels. It's kind of quite dense pseudo labels, but we only use the most confident ones to supervise the stereo matching.
And the voting is picking the most confident ones?
Yeah, only to pick up the most confident ones.
Okay, so then we have basically a labeled data to work with for deep learning purposes.
Yeah, exactly.
Okay. Cool.
We also built something based on Raft, the best paper on ECC 2020. So this network, we call it like OPT-Stereo. So OPT-Stereo first builds on multi-skew cost volumes. I put it M0 and M3. So then we adopt our recurrent unit to iteratively adapt the disparity estimations at higher resolution. So it's a kind of based on the traditional methods, we bring something from traditional methods. So we try to use a kind of cost to find paradigm to achieve better efficiency. So this one, we use this kind of algorithm, we can achieve better efficiency and also better accuracy. I put a demo video here, so we also tested several different sequences. So you can see that our algorithm performs very robustly, and also you can find some errors. The most errors exist on the near the sky, because for skies we can typically we cannot always get the ground truth labels. The ground truth, because for example, like skies, it's not too many features. The most features are on the for example, like cars, buildings, trees. So we cannot get pseudo labels for the sky. We cannot supervise the network to train some good disparity estimation for the skies. So let me continue. So I discussed the optical flow estimation and stereo matching. So now I want to discuss the surface normal estimation. So we believe surface normal is a kind of important and also an informative 3D information. There are two different types of surface normal estimation approaches. The first one is based on geometry based. If you work on some like point cloud based surface normal estimation, you will know like typically they typically if they want to discuss if they want to estimate the surface normal of this point, they typically select this point and then select some neighboring points, and then they do some like local plane fitting, for example, like to fit the points into a quadratic plane or like a planar surface, and then the surface normal of the plane will be considered as surface normal of this point. And for geometry, for the machine deep learning based methods, typically they have different regression models. And then, for example, like this one, they use CN to estimate depths and then depths to normals. And then so the normals are typically estimated with some like CNs. So it's not explainable. But they do not really care about surface normal estimation. They care more about like, for example, depth estimation or like scene understanding. So surface normal estimation is only used a small part for this kind of methods. So in the last year, we proposed a geometry-based method called 3 filters to normal. So as its name says, we only use 3 filters. We use 2 image gradient filters, and also we use a median or mean filter. So you can see from this kind of image, I put RGB images on the bottom, on the top, and then we put some examples for disparity images and also depth images. The left are the depth images. The right are the disparity images. And the bottom are the surface normal maps. So typically we use 2 different, so we use 2 image gradient filters. For example, the image gradient filters like from Sorbo, from Kenny, from some other edge detection algorithms. And also with a mean filter or media filter to estimate NZ. Because for image gradient filters, we can only use them to estimate NX and NY. So we need to use NZ with media or mean filters. We also compare our methods with all SoTA geometry-based methods, including plane PCA, plane SVD, false SI, etc. So we compare, I guess, 9 SoTA algorithms. And our algorithm demonstrates the SoTA performance, outperforming all other existing geometry-based surface normal estimators. And in terms of both the trade-off between speed and accuracy, and also the accuracy. For example, if we use mean filter, our algorithm can achieve the best processing speed. But when we are using the median filter, our algorithm can achieve almost the best accuracy, except for angle-weighted algorithm. And we also evaluate the trade-off between speed and accuracy. And our method, the FD mean, achieves the best trade-off between speed and accuracy. And also we publish our code and our data sets on GitHub. So we publish our MATLAB code, C++ code, and also CUDA code. Our C++ and also CUDA implementations achieve a processing speed of over to 30 Hertz and 21 kHz. So I mean, to 30 Hertz means we only run the algorithm with C++ on a single thread CPU. For 21 kHz, we run it I think 2080 time. Here is a demo video.
Sorry, short question. If I may interrupt, is it supervised or unsupervised?
So it's a good question. I think we cannot say it's supervised or unsupervised. So typically it's geometry based. So it's I think it's based on mathematics. So if you get the depth images and get the like intrinsic matrix, you can directly get the surface normal maps.
Okay, so you basically don't have any information.
We don't have any.
About...
We don't have any.
Okay.
We don't have any training strategies.
Okay. Thank you.
It's not based on. It's not based on science. It's based on like geometry. So let me continue to share another demo video. So typically, we did some kind of ablation study, but I think it's not good to see ablation study because we try to use different image gradient filters, for example, like BG, Sobo, etc. And also we try to compile the mean filter and the median filter. So you can see that this one means the errors. So we created 3 large-scale data sets, including I think 30K images. So we created 3 data sets. One is easier, medium, and also hard. And also we compare our method with some other SoTA methods. So the first one is for ablation studies. You can see what we also create some like indoor, outdoor, etc. So we download some like 3D models from online, and also we use OpenGL to render to get the depth images to get the surface normal ground truth. Our source code and also the data set are published. This means that we compare our method with some other SoTA methods. And you can see that for plane SVD, plane PCA, and vector SVD, angle weighted, and also area weighted, this kind of method is based on point clouds, so it can bring better accuracy, but the time, the processing speed is very long, so the efficiency is very low. But our algorithm, you can see from this one, we use a median filter, but our method can achieve a very similar accuracy, but our processing speed is much faster. I think too many experiments. Let me. Can also so we also evaluate our methods on some other public data sets with like depth images. So basically, our method only to input one depth image and to output a surface normal map. So it's kind of end-to-end translation, but we do not use any like science to train it. So typically, it's based on mathematics. So we find a kind of solution to translate a depth image or disparity image directly to surface normal. So I can also so a lot of kind of like experimental results. So I can go faster. So we also try some like different data set like Sincere. This one is for autonomous driving. You can see based on this one, I think we found something like, for example, like for Freespace or for road, the surface normals are always similarly, also similar. So we, inspired by this one, we developed a free space detection algorithm. I will show it later. So we tested our method on different synthetic data sets. Also, we tested our method on TT. So this one is a disparity images. We use, I think, PSMNet. We use PSMNet to estimate disparity images, and then we use our method to translate the disparity image directly to the surface normal. And also, you can find the road area. I mean, the free space detection. The free space can be very easily recognized with surface normal. And also we try some depth images, I put depth images. So we use a monocular depth estimation algorithm to get depth images. Let me go. So finally,
one more short question.
Yeah, sure.
If you can,
don't worry.
Yes, for free space detection in practical applications, it's very important how fast you can detect. So there was a slide when you showed the performance of the network. How fast is processing power?
Do you mean surface normal estimation?
Yeah.
So first, I can go back. I think it's better. So you can see, like for C++, I think it's like i7 CPU. It's like 230 hertz, and for CUDA it can be like 21 kilohertz. So it's very fast. It can be ignored. Yeah,
that's real time. Thank you.
Yeah, I think it's faster than real time. So I think typically real time should be like 40 frames per second, right?
Well, yeah, you also have lots of other networks, so you always sum them up. But for real time, it's kind of very good achievement. Yeah.
Yeah.
What's the resolution, just to make sure?
So I think here I think it's for 640 and 48 for this kind of values. For this, I think it's 640 and 48, 480. I think it's faster than real time. So this is why we put the title as ultra fast surface normal estimator. But let me share the last example. So typically, the last example shows that surface normal is very informative information. It can also be used to help 3D reconstruction. We also evaluated our method for 3D reconstruction. So typically, we do the SLAM with and without surface normal information. So it demonstrated that surface normal can bring better 3D reconstruction or results. So I think it can be kind of 60 information when doing when doing this 3D reconstruction. So let me move forward to the next slides. So for driving understanding, let me go faster. So I typically posted two different big pictures. The first one, semantic segmentation, the other one, object detection. So my group is mainly worked on semantic segmentation. So for semantic segmentation, typically we try to assign each label with which we try to assign a label to each pixel. So for example, you can see from this image, the purple areas means the road, and the blue means the car, and different color means different classes. So for free space detection, it's very important component for autonomous driving perception, because for free space can also be used by other modules like prediction, planning. Because free space bring provide kind of drivable area. For free space detection, it's kind of a binary semantic segmentation problem. So typically, we try to do semantic segmentation, but we have only two labels. We have only two classes, like 0 and 1. 1 means free space, and 0 means others. So typically, we use semantic segmentation algorithm to solve the free space detection problem. So in the last year, we developed a normal free space detection algorithm called SNE-RoadSeg. So there are, I think, three contributions, but I only listed two here. The first contribution is we developed a novel module named surface normal estimator. It's based on three filters to normal. It's based on the previous mentioned surface normal estimator, but it's based on energy minimization. So we put the surface normal estimator here, so it can translate a depth image or disparity image to surface normal map. And then we try to fuse the surface normal map and also the RGB image to with two encoders, and then to fuse these two and then to fuse the two different features, and to get better semantic segmentation results. So it's kind of data fusion CNN architecture. This one is called RoadSeg. So this one is called SNE. This one called RoadSeg. So we call it the SNE RoadSeg together with this whole method. So this is a block diagram of the surface normal estimator. So typically first we should translate a depth image into an inverse depth image. So this kind of inverse depth image is like disparity image. So then we use two convolutions. One is for horizontal image gradient filter. Another one is for the vertical image gradient filter to get the GX and GY. It means the horizontal and vertical image gradients. And then we can use this one to compute the surface normal. The surface normal will be NX, NY, and NZ. So we formulate this one as I think with this equation, and then we incorporate this one into energy minimization problem, and then to solve this problem to get the best surface normal, and then finally the optimum surface normal map will be like this. This is our demo video. Let me show you. So typically, we run our method on the KT road benchmark. So, but for KT road benchmark, it's a big challenge, but it's a very it's easier than Cityscape. So upon submission, our SNE-RoadSeg was ranked the second on the KT road benchmark. The green areas means the Freespace. This is only for testing. So we only used I think 200 images for training. We also evaluate our method on two synthetic data sets. This one is Sincere, I think published on BMVC. So you can see that our algorithm works better than synthetic data sets, because for synthetic data sets, it's more ideally. It's more ideal, so provides it's a less challenge. So one problem for our algorithm is we have to use RGBD data. We have to use RGB images and also depth images, for them, or depth or disparity images. So our next step is to use only RGB images to get something similarly. So this is our data set called Ready to Drive. We created all this data set on color. So we typically try to demonstrate that our algorithm can also perform well on different weather and illumination conditions. This one, for example, like sunny and rainy. We also put some other different weathers. So let me move forward. In this year, we developed a more advanced version called SNE-RoadSeg Plus. So typically, we have two different modules as usual. So we have SNE Plus, and also we have RoadSeg Plus. So for SNE Plus, we find a more we find a better formula to estimate surface normal. And for RoadSeg Plus, typically we use deep supervision to help the network to learn the free space more efficiently and accurately. And also, this algorithm is currently ranked the first on the KT road benchmark. In addition to the data fusion semantic segmentation, we also explored how to use multiple views, but use only one single camera to improve semantic segmentation, to improve the single model semantic segmentation. So we only use RGB images to train the semantic segmentation. So typically, we found that homograph matrix can be used to translate two images. This is two stereo images. This one I think is for left image. This one is right image, probably. And then we try to translate the target image into the reference view, so that we can input two images into the network, and then we can use two images to improve the free space detection accuracy. Here are some quantitative and quantitative results. So you can see that when using this kind of data augmentation method, all the metrics can be improved and all the networks can be improved. So we typically, I think we compile all the SoTA single model CNNs. And also you can see that our method performs more robustly when using this kind of data augmentation method. In addition to the free space detection, we also did something for road anomaly detection. So it's kind of small objects on the road. So we are working on this one because we have a project for automated ground mobile robots, such as like robotic wheelchairs. So currently, the public benchmarks like KT and Cityscapes are not designed for the kind of small objects. So we have to create some benchmarks for this kind of tasks. So in the last year, we developed a data fusion network to jointly detect road anomaly and the free space. So typically, similarly, we use soft normal to help the road anomaly detection. So it proves that soft normal can also be used to detect road anomalies. But in this year, we also explore different data fusion networks with respect to different vision sensor data, including RGB images, disparity images, normal images, HHA maps, and also elevation maps, and also transform disparity images. So we try to explore which type of visual information is the most informative for road anomaly detection. So based on our experiments, we try to use different visual informations and try to do different semantic segmentation. So typically our conclusions are, first, data fusion networks are more robust than single model networks. You can see that we compare our single model networks, and also we compare the data fusion networks. And also we found transform disparity images. I think this one is transform disparity images. This one is the most informative. This one is better than other visual informations. So if we want to do road anomaly detection, we have to. It's better to use transform disparity images to do to fuse with the RGB images. So if we get the free space, we get the road, so we can analyze the road with support for some other features. So for this kind of project, it's my first project during my PhD. We did something for lane marking detection. So it's kind of lane marking, lane detection algorithm. So instead of doing like lane detection from images, typically I think most algorithms try to detect lanes from like image. It's a kind of image based. Try to get image features, like for example, like use edge detection, Hopf transform to get the lane markings. But our algorithm tries to use the vanishing points to model the lane direction. So typically, we use a stereo vision camera to get the disparity image, and then we try to project the disparities to get the video disparity map, and then we try to estimate a vertical vanishing point and also a horizontal vanishing point. So then we'll use two different equations now for horizontal and vanishing points to get the whole lane directions. And then because we know the lane directions, so we all know the lane markings. You can see this one is with disparity image. So the vertical vanishing point will be here. So it's corresponding to here, this line. So this line will be the horizontal vanishing point. It will be the vertical vanishing point. So it will be get the interaction here. So typically, some people use like Hopf transform to extract this line and to consider this one as a straight line, and then they will do like Hopf transform and to get the equations of this line and to get the intersection. But we consider this.
Wait, I think for like 2 seconds there we couldn't hear you. Something with the half transform.
Hopf transform. Oh,
yeah.
Okay. Okay, so I think for basically, I think for originally people use Hopf transform to detect this line. They consider this one as a straight line, but we consider this one as a quadratic line because sometimes will be up hills and also down hills. So we'll consider this one as a quadratic line, and so we use dynamic programming to extract this line, and then we will use least square fitting to get the coefficients. So after get the vertical vanishing point with dynamic programming and also least square fitting, we also use a very similar strategy to get the horizontal vanishing points. But the length will be curved, so it will be multiple vanishing points. For example, you can see if you only see the bottom row, the vanishing point will be something here. But if we go upper, so the vanishing point will be here. So the vanishing point will also change. So it means the lane direction will change. So we use similar strategy to get the horizontal vanishing points, vanishing points. So it will be a group of vanishing points, and then we'll use this one to get first order equation, and then we use previously estimated quadratic line and also the first order equation to get the whole lane direction. Let me play this kind of demo video. So you can see our algorithm works for both the straight lines and also curved lanes. And also we do not need to split like horizontal and also curved lines. Original people have to consider that horizontal line, the curved lines should be estimated with for example, like a parabola, and for the straight lines should be estimated with like straight lines. But in our algorithm, we only to use two equations to get the whole lane markings because we get the lane directions. So finally, for driving scene understanding part, I would like to briefly share one of our recent works for air-ground cooperation. So typically, we try to detect some parking violations. The parking violation means the illegally parked cars. For example, like these two. Let me use laser pointer. So for example, like these two cars, they are illegally parked. So we are trying to use a UAV and also autonomous driving car to get the parking violations. So typically we developed a kind of a framework. It's called like suspicion and investigation framework. So it has two phases. The first phase is to get the illegally parked car candidates. The second one is to verify that whether the candidates are true illegally parked cars. So this is a demo video, so I can play it. So typically, the drone is landed in a mobile airport. We have robot arm to replace its battery. So when the car arrives at the target location, the UAV will take off to detect parking violations. So typically, the UAV needs to fly for two loops. The first loop is to get the possible parking violations, and then when the UAV flies to the second loop, when it arrives at the same location, if this car is still there, so it will consider this one as a parking violation. So typically, we also use optical flow estimation here, because for example, there are some dynamic cars, some moving cars. The moving cars will be considered as illegal parked cars if we do not use optical flow. Optical flow is only used to remove the dynamic objects. And the blue bounding boxes means the illegal parked car candidates, and the green ones means the legally parked car candidates. We also use ORB slam to build the map to localize the cars.
And we may assume that the drone doesn't fly autonomously, right?
It's not autonomous. The drone has to be run by a human. It's moving up and down.
William, we had the question about the vanishing point part with the lane detection. Is it okay to ask now, or can we ask
yeah,
later?
Sure. Let me just give me a second. Let me post this one. Yeah, please.
So Ina was asking for the vanishing point algorithm. Was it run per frame?
So I didn't catch you. So what do you mean? Let me go back.
So if we have a video input, each frame, we calculate the entire optimization process per frame, or do we have a way to optimize over the frames?
I think it's for each frame. So typically we have two images. We have kind of left and right images. So but only the right image only used to get the disparity images. So if you have a depth image, it's fine. You can only use one image. So typically it's frame by frame. It's not like iteratively.
And what's the runtime there if we have an optimization process per frame?
This one, I think the previous one, our first version, I think published on 2016, should be kind of, I can't remember, maybe several frames per second, maybe like 5 to 10 frames per second on CPUs. And then in 2018, I published another work. I implemented the algorithm on the GPU, so it can run in real time.
On that 64 pixel by 100 pixel, something like this, or?
I think this one, I think for KT, I think 375 by, I guess, 1220, I guess. Something like 1200 and 370, I guess, something like that.
Wow.
This one is a KT, it's a KT data set.
Interesting. Okay, cool.
So if you're interested, I can also send me an email. I can share the other two papers.
So let's say yes, share. Send it to me. I'll post it also on the YouTube recording.
Yeah, sure. Let me go back. We can see the first one. It will be the suspicion phase. It tries to get the illegally parked car candidates. And you can see that then it will change to investigation phase. So investigation phase, it will verify each candidates. So we can see the red qubits. It will be the true illegally parked cars. So we typically use this kind of algorithm to detect the illegally parked cars. Let me move forward because I think we still have like another section. The second section will be the road condition assessment. It will be still also a major part of my research. And typically we try to get two different tasks done. The first one is to reconstruct the 3D geometry of the road surface. The second one is to detect the road damages. So I can put some like video. I put some videos here so I can show you some like different videos, some different cases. So this kind of videos, I think, can explain why road condition assessment systems are very important. If you have a car, you should have a kind of bumpy driving experience when hitting potholes. For example, like the UK government spent, I guess, tens of millions of pounds to inspect and repair roads. This is why we need automated road condition assessment systems to reconstruct the 3D road surface and also to detect the road damages. And we can also recognize, we try to recognize and also localize the road damages both efficiently and objectively. So I put some like kind of background here. So road inspection is a critical task for road maintenance because it can ensure traffic safety, allow governments to apprise long-term investment schemes, and also to help governments to allocate limited resources for road maintenance. But currently, you can see from this image, manual visual inspection is still the main form for road condition assessment. So typically, the inspectors have to move around to detect potholes. So we're trying to detect kind of automated system to detect potholes. Because for this kind of detection results, it depends entirely on the inspector's experience. It's kind of subjective. And also, this kind of process is time-consuming, tedious, and also expensive, and also dangerous for the inspectors. So there are three kind of sensors used for road condition assessment and also road surface 3D reconstruction. The first one is the layer scanner. The second one is Microsoft Kinect. The last one is stereo camera. My group is mainly working on the stereo cameras. So the first one, the layer scanners, the results is more accurate, but the problem is the purchase of the scanning equipment and its long-term maintenance is very expensive. And this has to be mounted on a kind of vehicle like this one. It's called a kind of inspection vehicle. So we cannot only purchase a LiDAR scanner, we have to buy the whole vehicle. As for the Microsoft Kinect sensor, kind of it's good, but it's cheap. But the problem is it can greatly suffer from infrared saturation in direct sunlight. So my group is trying to use stereo cameras to get very highly accurate 3D reconstruction results to detect potholes. Because stereo camera is cheap, and also it can overcome some difficulties faced by the Microsoft Kinect sensors. So in 2018, we proposed a novel dense subpixel disparity estimation algorithm for dense low surface 3D reconstruction. So we have three main contributions. The first contribution is perspective transformation. The second one is subpixel disparity map estimation. The last one is disparity map global refinements. This is our experimental setup. So typically, we are trying to use this kind of stereo camera to get the whole 3D road geometry models. So for the perspective transformation, typically we have these two images are captured by stereo camera. So this one is the left image. This one is the right image. So you can see these two images look different because you know they are at different locations, different positions. So our algorithm is trying to transform this original right image to the transform right image. So if you compare these two images, for example, the original left image and the transformed right image, so these two images will look similarly. So if we compare these two images to get disparity information, the cost will be lower. So it can get more confident disparity estimations. So typically we do disparity transformations for the original left image and also the transformed right images. And also we do disparity transformation for the disparity estimation for the original right image and the transformed left image. So we'll get two different disparity images. So this kind of algorithm can bring better efficiency and also speed. For disparity estimation, typically we are based on kind of sample size. So from this image, you can see that the road disparity is also is very smooth. So it changed gradually from the bottom to the top. So typically we use an iterative method to estimate those disparities from the bottom to the top. So typically we only estimate the disparities. We use whole search range to estimate the disparities only for the bottom row, and then we propagate the search range from the bottom to top. And from each iteration, we only use 3 neighboring points to suggest the search range. So only use 3 neighbors to get only several disparities. So it will kind of based on the concept as what I mentioned before for sparse cost volume. So we only build sparse cost volume to get the disparity image. So this is our experimental results. So this one is RGB images. This is one are the disparity images. So you can see that we can clearly find the cracks and also some like geometry features from this kind of images. And also the road cracks are very clear. I put a demo video here. So this one is this red block is a region of interest. So I just select a region of interest and to zoom in to show it more clearly. So this one is a reconstructed 3D geometry model. And the reconstruction accuracy is 3 millimeter. So just before doing these slides, I just create another video with this one. So I guess this one is better to show how accurate our reconstructed 3D road surface is. Let me change this one to play it. So I just use this one. I use MATLAB to show this one. I zoom in and you can see this one is reconstructed 3D road geometry models. And the pothole areas are very clear. So you can find the shape, geometry reconstruction, the geometry structure, and also the depths. the accuracy is 3 millimeter. And after that, I think in 2019, we submitted a paper with better accuracy. I think the current SoTA method is 2.23 millimeter. So imagine that if you can get this kind of 3D information, 3D geometry model, so it will be very easy to get the pothole areas. In 2019, we optimized our method and implemented this whole system on drone to acquire 3D road geometry models. So these experiments were conducted at HKUST, and we used adjacent TX2 GPU to produce the disparity images. So so typically we embedded a GPU and also still camera on the drone. So the drone will, so the still camera will always look at the road area. This one is the left image. The reference image means the left image. Target image means the right image. Because no, we do not know which one is the left, which one is the right. So we just try to rename them as the reference and target. This one is the reconstructed road surface. We also run ORB SLAM on this data set. So eventually, this kind of system can not only reconstruct the 3D road geometry models, but also can detect and localize the road damages. So we are trying to build a vision-based road damage detection and localization system. We do not want to use some other sensors like LiDAR, GPU, GPS. Because in some cases, GPS does not work. For example, like between the buildings. So we use the ORB SLAM to demonstrate whether it's enough to use only road images to reconstruct the whole city map. So the conclusion is yes. So if we only use the images, if we only use the road images, it's enough to localize the drones and to build a 3D environmental map. So we also put some quantitative results. So eventually we can we can use a drone. We can only use a still camera to localize the road potholes and also to mark the potholes on the map. So in 2019, we proposed a hybrid road pothole. Thank you. And in 2019, we proposed a hybrid road pothole detection system. So typically, this system is based on 3D point cloud modeling and also based on some like 2D image processing algorithm. So typically, we can get the disparity image we use by using the previous algorithm. And then this one is not very clear to see the potholes. So we developed another one called disparity transformation to transform this image to the other one. So you can see that the pothole areas is very clear from this image. And then we use also, I think on the other slides. So we use also thresholding method to extract this kind of potential and damaged road areas. So we only use the disparities in the purple areas to fit another disparity model, a disparity map. So by comparing these two disparity maps, this one, the original disparity map and the model disparity map, so we can find the pothole areas. And then we can just extract the pothole areas. We can extract the 3D point clouds. You know, in recent years, the traditional methods is not good enough for some like scene understanding problems. So in addition to the traditional method, we also explored how to use different attention modules, semantic segmentation, and also use GAN, generative adversarial domain adaptation to augment the training data and to compare the performance between single model and data fusion CNNs. So we try to use semantic segmentation to get the potholes. So currently, I think CNNs will be the future of this area of research, but we still need more data. So recently, we proposed a novel pothole detection algorithm and also a benchmark. So we first discussed the SoTA CNNs designed for semantic segmentation and evaluated their performance for road pothole detection with extensive experimental results. And also, inspired by the graph neural network, we developed a novel layer called GAL, graph attention layer. So GAL will be able to be embedded in any semantic segmentation network. So we embed it here. So if we embed GAL in a semantic segmentation network, it can help the semantic segmentation network to get better learning representations. So with this kind of images, we also show that our method can also be used for other applications except for potholes. We also try some other like self-driving and also endorsing understanding problems. And based on this kind of evaluation matrix, as you can see that all the evaluation matrix can be improved and all the CNNs can be improved. And also we also put some like visualization. So these are the corresponding main activation maps of the features after the last layer of the encoders. So you can see when using the GAL graph attention layer, the semantic segmentation network can learn better learning representations. And also the good news is this kind of layer can also be used in any semantic segmentation network. So I think it's near the end, so the summary. The summary will be recent AI technologies, for example, like deep learning, have greatly enhanced the machine learning, machine vision applications from driving scene understanding to road condition assessment to clinical diagnosis. The combination of CNNs and traditional method, as I mentioned before, if we bring something from traditional method, for example, like stereo vision, we can design some interesting method, for example, like self-supervised or unsupervised methods. And for semantic segmentation, data fusion networks can provide better accuracy on scene understanding, but we still need to do some other improvements. For example, we can use knowledge distillation to get more applicable to some for some cases when we only have the RGB images. And for road condition assessment, typically with machine learning and also deep learning algorithms, it will be a popular research area that requires more attention, and also it will be the future. It will be the future, and also we need to consider the computational complexity when implementing AI algorithms on resource-limited hardwares. For example, because for autonomous driving, we need to run everything in real time, so we also need to consider efficiency when developing our algorithm. Thank you very much for your attention, and I'm more than happy to answer any questions.
In the meantime, I'll say thank you, Louis, for a very elaborative talk and informative, really, seeing all of it run in real time. And that is such a low resolution. With good results is quite impressive.
Yeah, we are trying to do everything on our resource limited hardware, because we have autonomous cars, we have drones, so we need to consider kind of robotics applications.
Yes.
Mm-hmm.
So dynamic programming per frame running in real time.
Yes, I can share another paper. The other paper, I think, only do some incremental improvements, so I didn't put it on the slides.
People in the audience, this is your chance to shine. If anybody has a question, speak now.
Yeah, can I ask a question, please?
Yeah, please. Yeah.
So I'm interested in like better understanding formulation of a road condition assessment.
Yeah.
So you take you capture images by drone, and the images are taken above the road, or it's like from the vehicle. This is what I didn't because I think it had two formulations, and
yeah,
and then the question is, when you trained the system, did you use like annotation by some annotation of the cracks over bad conditions or not? So it's not self-supervised. It's you needed some annotation, yes, if I understand correctly.
Yes, I think it's two questions. I think they are also very good questions. So probably I confused you. So I think for this one, the first one, we put a stereo camera on the car because you can see the cable. So we connect the cable with our PC. So we have a laptop on the car. So this one is the first system. So we put this one on the car because we have a laptop. But then for some cases we do not have the laptop, so we only have a kind of embedded GPUs like the Justin TX2. So this is why we need to develop something for the embedded drones. So there are two different systems. The first one is for the cars. The second one is for the drones.
But if I understand correctly, at least with drones, I understand that like the drone is almost frontal parallel to the road.
Yeah,
but but when it is like installed on the vehicle, it seems to me that you are very like sensitive to how the camera is installed. So I think that, let's say you have some system, but camera is installed differently on another angle. Do you think it will influence you somehow?
In my opinion, I think the angle will not make many difference. So if we just install the camera on the car, I think the results will be very similarly. But typically, we mount the car as particularly as possible to the ground, because now we want to capture most of the view of the ground. We do not want to capture some other like vehicles or pedestrians. So you can see from this figure the experimental results, the experimental setup. So you can see this angle. So we try to use the camera to look at the ground, only to look at the ground. We do not care about like pedestrians and also vehicles. And let me answer the other question. So this is two questions. I think for these two algorithms, one is based on this one. This one is based on this one is designed for the cars. The other one is designed for the drones. This one, both of these algorithms are based on traditional methods. They are not based on CNNs. So typically, we use mathematics to calculate the 3D geometry.
And so everything that it's not planar is considered as being like bad road condition, if I understand correctly.
Yeah, currently we try to get the 3D information to detect potholes. Because, for example, like this one, I zoom in and then I rotated the point clouds. You can see the pothole areas. It's very clear, like the depth and also the shape. For example, like this.
Can I ask another question? Because it's really interesting.
Yeah, sure.
So usually, at least in our country, so the visually road condition is okay until it's raining. And when it's raining, so in a few minutes, or not few minutes, but in an hour, you can have damaged road, but because of rain, but because of the pools, you can't see them. So the problem is not only like, so I don't see how visually we can find that there are pools, and these pools are very deep because, and this is, so it's interesting to me how do you want to solve the problem when you want to define road condition in the rainy, when it is rainy, and what are you going to do in this case? Because you can't see it using like only visual cameras. It depends on
to this. It actually, you can also add any type of thing that obscures view. If there are debris on the road, sand, salt, ice, rain, everything that makes it unclear what's behind. Yes.
Yeah. So I think it's a very good question. It's very practical question, because we didn't consider about rainy days. So I think for inspectors, they will not do road inspection during the rainy days. So typically, I think we didn't consider too many about the extreme conditions. So typically, we just do it in sunny days.
And so in a way, it's like not very economical, because you have a system on each vehicle, and so on each vehicle the system is running to find them. But So this is exactly my view that all vehicles should collaborate information. It's enough that one vehicle just knows that something is not okay, and it's transfer information to all vehicles behind.
Yeah, it's a good point. So currently we are trying to develop kind of smart machines. So we're trying to mount these kind of machines on all the vehicles, on a lot of the vehicles. So we are trying to use several vehicles to build the whole city. So my project is working on the detection right now. So after that, my project and also my team is trying to work on some kind of evaluation. So we are trying to build the whole city, and also, for example, like January, February. So we are trying to predict the conditions in the future. So I think it's good points. So I think we cannot just mount the machine on only one vehicle.
And also another question, it's like more relevant to the first, I don't know if it was in the middle, but at the point when I started, when I attended, when you spoke about free space where you can the road itself. And so my question is, it's like, yeah, exactly. So you already, it was before. So do you think that it somehow depends on how roads are constructed in some different countries? Because, for example,
it's a good question.
Yeah, because for example, curbs height is different in different countries. We also mark them differently. So it's interesting to me what people are doing in this.
It's a very good question. So I think we considered about this one, but we only tried US, China, and UK. We didn't try some other cases. So problem is in some cases, they have different structures and they have different rules. So probably I think we need to develop some algorithms specifically for the country, for this country. Yeah, it's good. It's a very good question.
And also another question. So this is more in your summary. So in summary, you thought that currently we need less and less data because there are more self-supervised methods that can be used. So can you to deep in this a little bit more? What do you actually mean?
Oh, I see. I got you. So we are trying to use some kind of traditional methods. For example, I can use a stale matching as an example. So for stale matching, typically for traditional method, we just do mathematics. For example, we select one block from left image, and then we select another block from the right image, and then we just do stale matching, and to get the estimation. So the problem is the results is not very good, and also, but the problem is we do not need any ground truth to train the model. So typically, we are trying to bring something from traditional methods to develop some kind of strategy to get the pseudo labels, some confident labels. This kind of labels can be used as ground truth. So we do not need any ground truth later on. Okay. This is what I mean.
Okay, I got. So you mean that the classic, you want to use classic methods to create labels for deep learning in a way?
Yeah, so it depends on different texts. For example, for stale matching, we typically use a classical method to get the pseudo labels.
Okay, good. Thank you.
Any other questions?
I think people had a chance to think and write. Probably no other. Rui, you can, if you have any words to summarize, go ahead, and then I will finish with mine also.
Yeah, so the last, maybe the last comment of mine. So when you speak about, for me, it's like straightforward that when you use fusion methods, you get better results. Because for me, theoretically, it's like ensembling. But usually people don't use ensembling because you need to run more models and its power and so on. So it's good for showing results, but what do you think will be done in practice in the future? Because no one will want to run many models simultaneously.
Sorry, I didn't catch you too much. So can you just to explain it?
Okay, so you thought that when you use fusion, different people.
Do you mean like data fusion for different kind of visual information?
But do you fuse only information or you fuse neural networks results? This is my
no. Currently, we are trying to fuse the kind of features. We try to fuse all the learned features, and then we try to use the fuse features to get a better semantic segmentation prediction. So typically we have two encoders, which each encoder is to use to extract features, and then the extracted features are used to the extracted features will be fused.
I got you. Okay, thank you.
It's not only the images, not only the like results.
Okay, got you. Thank you.
Okay, everybody. I think we're gonna wrap this up. As usual, thank you everybody for joining and taking this time and joining the talk. Thanks anybody who's gonna watch this recording after. You can post us a comment and let us know what you think, or join the next events. You have other places where you can find the community everywhere, both on Meetup and YouTube, so you can check there. Aloy, again, thank you for coming today and giving this talk to us.
Thank you for the invitation.
And this is a good time for me to ask you and the audience if you know of other interesting speakers in our field who would like to give a talk, who have something interesting to share. Please let me know. It's hard to find quality content for us. So if you have any references, please let me know. I'm always very happy to hear. Yeah, and with this, I will say thank you, everybody. Have a good morning, good evening, good day, wherever you are. And until the next, and until the next time. Thank you.